Hi students, as you know, NDA has introduced a new unit in the chemistry syllabus for both the NEET and JEE from the year 2024 onwards. The new unit included is the principles related to practical chemistry. Since it is a newly introduced topic, the necessary study materials may not be available in print and visual media. But you need not worry. I am uploading video classes through my YouTube channel explaining the theory related to chemistry practical, which include a lot of multiple choice questions and their well explained answers. By the way, I am Dr. Syriac Matthew, a retired associate professor in chemistry. The purpose of my channel, Chemistry Master, is to upload video classes related to topics in chemistry within secondary, undergraduate, and postgraduate levels. At present, I am uploading video classes related to NEET, JEE Main and Advanced, and other entrance examinations. There will be a set of video classes for each chapter. In the present set of videos, we discuss the principles related to practical chemistry. This set includes 6 video classes. The first one, titled as Principles Related to Practical Chemistry, Part 1A, explained detection of extra elements and detection of functional groups. The second, titled as Principles Related to Practical Chemistry, Part 1B, contains multiple choice questions related to Part 1A. Part 2 explains preparation of some organic and inorganic compounds and a titrimetric analysis. Part 3, qualitative analysis for anions, and Part 4, qualitative analysis for cations. The Part 5 explains some physical chemistry experiments. At the end of each part, multiple choice questions related to that part are explained. Even if you go through a handbook of chemistry practical several times, you may not be able to remember the experiments and the theory behind it. But an audiovisual presentation will catch your attention. That is why I have introduced a lot of animations in these video classes so that you will get a feel of doing the experiments in the laboratory. However, animations never represent the real situation. And this is not an instruction manual for doing the experiments in the lab. The main purpose is to make you understand the theory behind the experiments. In the laboratory, you have to take several precautionary measures while doing the experiments. For your convenience, I have introduced video chapters or timestamps in the description part of the videos. This will help you to watch and rewatch separately the different topics explained in a particular video. The links for other videos are also given in the description part. You can easily move to any of these 6 videos using these links. I hope these video classes will definitely help you to understand the theory behind the experiments. If you like the video, please subscribe my channel and forward to others. You can expect similar video classes from other chapters of Class 11 and Class 12 Chemistry soon. This is part 3 of the 6 video classes on principles related to practical chemistry. In this video, we discuss chemical analysis, especially qualitative analysis. Under qualitative analysis, we consider analysis of anions. Everything is made of chemicals. Chemical analysis provides answers to 2 important questions. The first one, what is it? Second question is, how much is it? And the first question is the qualitative analysis, and the second question is the quantitative analysis. Qualitative analysis tells us what chemicals are present, and quantitative analysis tells us how much are the chemicals present. Knowledge of chemical composition of many substances is important in our daily lives. Analytical chemistry plays an important role in nearly all aspects of chemistry, for example, agricultural, clinical, environmental, forensic, manufacturing, metallurgical, and pharmaceutical chemistry. Qualitative analysis is a type of chemical analysis in which the identification of constituents present in an unknown sample mainly based on chemical methods. By constituent we mean anion and cation present in an unknown salt. The separation and identification of anions and cations are carried out by precipitation, which is controlled by the solubility product principle. When a substance is precipitated from its solution, we have a heterogeneous system comprising the precipitated substance and its ions in solution. The solubility product principle is obtained by applying the law of mass action to the heterogeneous system. An example is the precipitate in equilibrium with its ions. When silver nitrate is added to a solution containing Cl- ions, silver chloride precipitates. The solubility of silver chloride is very little in water and is said to be a sparingly soluble salt. In such cases, there exists an equilibrium between the silver chloride solid and the dissolved silver chloride, that is Ag plus and Cl- ions in solution. Solubility. Among others, the solubility of a salt depends on two important factors. A. The lattice enthalpy of the ion in solution, and B. The solvation enthalpy of the ions in a solution. Lattice enthalpy is related to strong forces of attraction between the ions of a salt. For a salt to dissolve in a solvent, these strong forces must be overcome by the ion-solvent interactions. Solvation enthalpy of ions is the energy released in the process of solvation. It depends on the nature of the solvent. You have studied these topics in Unit 6 Equilibrium of Class 11 NCERT text. A salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than its lattice enthalpy. For example, consider the dissolution of sodium chloride in water. We know that water is a polar solvent. Oxygen, being electronegative, acquires a small negative charge and which is shown as two hands. The red balls represent oxygen and the white represent hydrogen atoms. So here we will have a small negative charge. We call it as delta negative. And consequently for the hydrogen atom there will be a small positive charge and we represent it as delta positive. And both the hydrogen atoms possess delta positive. The negative part of water molecule go near the sodium plus ion and the positive part go near Cl- ion and pull the two ions apart and separates them. Water molecules now surrounds the ions. Sodium ions are surrounded by negative part of water molecules and positive part of water molecule surround the chloride ions. This process is called solvation. Here the solvation enthalpy overcomes the lattice enthalpy, which is related to strong force of attraction between the ions. Use of solubility product principle. For a sparingly soluble electrolyte, an equilibrium exists between the precipitated electrolyte and its ion in solution. A sparingly soluble electrolyte means its solubility less than 0.01 mole per liter. As an example, let us take barium sulfate. It is a sparingly soluble salt in water. Now, a saturated solution of barium sulfate in water, there exists an equilibrium between barium sulfate solid and the dissolved barium sulfate, that is Va2 plus ions and SO4 2 minus ions. Now we can speak of an equilibrium constant and it is defined as K is equal to concentration of barium 2 plus into concentration of SO4 2 minus divided by BaSO4, barium sulfate, concentration of barium sulfate. And we know that for a pure substance, the concentration remains constant. So we take it as unity. So therefore this equation becomes KSP is equal to concentration of barium 2 plus into concentration of SO4 2 minus. SP means solubility product. An electrolyte precipitates when the concentrations of the ions, that is we mean the ionic product, in solution exceeds its solubility product at a given temperature. For example, copper sulfate is less soluble compared to zinc sulfate. By controlling the concentration of S2 minus, selective precipitation of copper sulfate can be achieved, and this can be done by adding HCl. H2S dissociates as 2H plus S2 minus. So there is an equilibrium between H2S and H plus and S2 minus. Now, when we add HCl, it completely dissociates into H plus and Cl minus. So the concentration of H plus increases, and the equilibrium is shifted backward, and consequently the concentration of S2 minus ions is decreased. Consider a solution containing copper ions and zinc ions. To that we are adding HCl. So there will be H plus and Cl minus ions, and the medium become acidic. Now we pass hydrogen sulfate gas through the solution, and this is the Kipps apparatus for generating hydrogen sulfate gas. The glass rod is dipped into the solution. Now we turn on the stopcock and passing hydrogen sulfate gas through the solution. A black precipitate appears. We close the tube. Here the zinc 2 plus ions remain in solution, but the copper is converted to copper sulfide. The ionic product of zinc sulfide is now less than the solubility product of zinc sulfide. And for copper sulfide, the solubility product is 6.3 into 10 raised to minus 36, while that of zinc sulfide is 1.6 into 10 raised to minus 24. So the solubility product of copper sulfide is very low compared to zinc, and therefore copper sulfide precipitates. Systematic qualitative analysis. We need to study only the following anions and cations. Anions: carbonate, sulfide, sulfite, sulfate, nitrite, nitrate, chloride, bromide and iodide. Cations are lead 2 plus, copper 2 plus, aluminum 3 plus, Fe 3 plus, zinc 2 plus, nickel 2 plus, calcium 2 plus, barium 2 plus, magnesium 2 plus, and ammonium. Inorganic salts may be obtained by complete or partial neutralization of an acid with a base or a base with an acid. In the formation of a salt, parts contributed by the acid are called anions, and the part contributed by the base is called cation. For example, in the salt copper sulfate, Cu2 plus ions is the cation and SO4 2 minus ion is the anion. Two important principles used in systematic qualitative analysis are A. Solubility product principle and B. Common ion effect. When ionic product of a salt exceeds solubility product, precipitation of the salt occurs. Ionic product of a salt can be controlled by common ion. It is called common ion effect. Depending on the amount of substance used, three scales of analysis are there. First one is the macro analysis. In macro analysis, we use 0.1 to 0.0 gram of substance and about 20 ml of the solution. Second is semi-micro analysis. Here we use 0.05 gram of substance and 1 ml of the solution. Third one is the macro analysis. In macro analysis, we use very small amounts of the substance and solution. Systematic analysis of inorganic salt involves the following steps. A preliminary examination, that is using easily perceptible changes such as smell and sight. Determination of anions using reactions carried out in solution followed by confirmatory test. Determination of cations using reactions carried out in solution followed by confirmatory tests. Preliminary examination. Preliminary examination will solve provide information which simplifies further course of the analysis. Preliminary examination involves noting the general appearance and physical properties such as color, smell and solubility etc. of the salt. And these are called dry tests. These tests are not conclusive but very often give important clues about certain anions or cations that may be present. Wet tests. Determination of anion or cation present by reactions carried out in solution. Solubility of a salt and the pH of aqueous solution give important information about the nature of ions present in the salt. If the solution of the salt is acidic or basic in nature, that shows it is being hydrolyzed in water. If the solution is basic in nature, then salt may be some carbonate or sulfide, etc. If the solution shows acidic nature, it may be an acid salt or salt of weak base and a strong acid. In this case, it is best to neutralize the solution with the sodium carbonate before testing it for anions. Gases involved in preliminary tests with a dilute sulfuric acid and a concentrated sulfuric acid also give good indication about the presence of certain anions. Heating with the dilute sulfuric acid is a preliminary test for the anions carbonate, sulfide, sulfite and nitrite. The list also include acetate, but we are not considering acetate here. First, let us consider carbonate. About 0.1 gram of the given salt or the given carbonate is taken in a test tube and 1 to 2 ml of dilute sulfuric acid is added. Now the test tube is fitted with an U-shaped tube and in the tube we take lime water. For carbonate there is no need of warming or heating. At room temperature itself carbon dioxide will be produced. And suppose that we gently warm the solution. The bubbles are coming out and the bubbles are due to carbon dioxide. And this process is known as brisk effervescence. Now the gas coming out from the test tube passes through this tube and it bubbles through the lime water in the U-tube. And lime water turns milky. If you are given sodium carbonate, when we add dilute sulfuric acid, sodium sulfate and carbon dioxide gas will be produced. Lime water is calcium hydroxide. And a carbon dioxide gas reacts with the calcium hydroxide giving calcium carbonate, and it is insoluble in water and appears as milkiness to lime water. Suppose that we are going on passing carbon dioxide through the solution, or we are passing excess carbon dioxide, the milkiness of the lime water disappears. When we pass excess carbon dioxide through calcium hydroxide, it is converted to calcium hydrogen carbonate. The calcium carbonate reacts with the carbon dioxide giving calcium hydrogen carbonate, which is soluble in water. And as a result, the milkiness disappears. Let us consider sulfide. And suppose that about 0.1 gram of the sulfide is taken in a test tube, and to that we are adding 1 to 2 ml dilute sulfuric acid. Now the test tube is fitted with a U-tube, and inside the U-tube we take lead acetate solution. And we gently warm the solution. And bubbles are coming out. And these bubbles are due to the formation of hydrogen sulfide gas. The hydrogen sulfide gas is coming out through the tube, and when it passes through lead acetate solution, lead sulfide is formed. So the lead acetate solution become black. Sodium sulfide, suppose you are given sodium sulfide, and sodium sulfide reacts with sulfuric acid liberating hydrogen sulfide gas. Lead acetate solution reacts with the hydrogen sulfide. and lead sulfide is precipitated, and this is black in color, and this lead sulfide turned lead acetate solution black. Hydrogen sulfide has smell of rotten eggs. Next we shall consider sulfite. As before, about 0.1 gram of the sulfate is taken in a test tube and about 1 to 2 ml of sulfuric acid is added to it. Now the test tube is fitted with a U-tube, and inside the U-tube we take acidified potassium dichromate solution. Now gently warm the solution. Bubbles are coming out. These bubbles are due to the formation of sulfur dioxide gas. The sulfur dioxide gas comes through the U-tube and it reacts with the acidified potassium dichromate and it turns it green. The reactions can be represented like this. Suppose that you are given sodium sulfite. Sodium sulfite reacts with the sulfuric acid, giving or liberating sulfur dioxide gas. The sulfur dioxide gas reacts with the acidified potassium dichromate, or acidified potassium dichromate oxidizes it to potassium sulfate and chromium sulfate. And chromium sulfate is green in color. So the color change is due to the formation of chromium sulfate. Next is nitrite, NO2 minus. As before, we take about 0.1 gram of the nitrite and add 1 to 2 ml of dilute sulfuric acid. Again, the test tube is fitted with a U-tube, but the U-tube contains acetic acid, potassium iodide and starch, or a potassium iodide starch solution. Now we gently warm the solution. Bubbles are coming out and it is due to the formation of nitric acid. Once the nitric acid comes out, it gets oxidized to nitrogen dioxide, and nitrogen dioxide is a brown gas. Now the brown gas comes through the U-tube and it passes through the solution and the solution turns blue. The reactions are, suppose you are given sodium nitrite and it reacts with the sulfuric acid and generate nitrous acid, HNO2. HNO2 is converted to HNO3 and nitric oxide is liberated. And the liberated nitric oxide, which is colorless, and it gets oxidized to nitrogen dioxide, which is a brown gas. In the U-tube, the nitrogen dioxide gas dissolves in water and nitrous acid is produced along with nitric acid. Now this nitrous acid in acid medium converts iodide to iodine, and the solution may contain I minus also. So I2 and I minus combine together forming I3 minus. I3 minus forms a blue complex with starch and hence the color changes to blue. We can do the above test in another way also. If we heat solid nitrite with dilute sulfuric acid, reddish brown fumes of nitrogen dioxide evolve. Addition of potassium iodide followed by freshly prepared starch and acidification with acetic acid provides the blue color. Let us consider the confirmatory test for carbonate, sulfide, sulfite and nitrite, for which we have performed the preliminary test. Confirmatory test is a secondary test carried out after the preliminary test to confirm the presence of a particular ion in the given salt. Confirmatory tests for anions are performed by using water extract when the salt is soluble in water. If the salt is insoluble, we use sodium carbonate extract. Sodium carbonate extract cannot be used for testing carbonate because the extract itself contains carbonate ions. Therefore, we must use solid substance for it. Sodium carbonate extract is prepared in the following way. Take 1 gram of the salt in a porcelain dish. Mix it with 3 gram solid sodium carbonate and add 15 ml distilled water to it. Stir and boil the content for about 10 minutes. Cool it, filter and collect the filtrate in a test tube and label it as sodium carbonate extract. Confirmatory test for carbonate is done using aqueous solution of the salt or by using solid salt. This is because sodium carbonate extract contains carbonate ions. Take about 0.1 gram of the salt in a test tube and add dilute sulfuric acid. Bubbles start coming out from the solution. Fit the test tube with a U-tube with one end long. Immerse the long end of the U-tube in another test tube containing lime water. Gently warm the solution. Brisk effervescence occurs due to the copious evolution of carbon dioxide gas. And as a result, the lime water turns milky. If you go on passing carbon dioxide for some more time, the milkiness disappears. Suppose that we have taken sodium carbonate and sodium carbonate reacts sulfuric acid giving sodium sulfate and carbon dioxide gas. Lime water is calcium hydroxide. When carbon dioxide is passed through lime water, it is calcium carbonate precipitate. This calcium carbonate appears as milkiness. Now, if you pass excess carbon dioxide through the solution, what happens is the calcium carbonate is converted to calcium bicarbonate or calcium hydrogen carbonate, which is soluble in water. Next is confirmatory test for sulfide. Take about 1 ml of the extract and make it alkaline by adding ammonium hydroxide. Now add 1 or 2 drops of sodium nitroprusside. A purple color appears, and the appearance of the purple color confirms the presence of sulfide. Suppose that we took sodium sulfide and this is sodium nitroprusside, and a purple color is due to the formation of sodium thionitroprusside. This compound is purple in color. For sulfide, there are 2 tests. First, we take about 1 ml of the extract, water extract or sodium carbonate extract in a test tube and add barium chloride solution. White precipitate appears. Transfer a small portion of this precipitate to another test tube. Now add dilute HCl to the remaining portion of the precipitate. It dissolves. And a sulfur dioxide gas also is produced. So if you are given sodium sulfite, when barium chloride is added, it is converted to barium sulfite, that is white precipitate. But barium sulfite is soluble in dilute HCl and it is converted to barium chloride and sulfur dioxide. To the precipitate transferred to the test tube in the previous test, add a few drops of potassium permanganate acidified with a dilute sulfuric acid using a dropper. The Kamenever solution get decolorized. So the drop become colorless. Kamenever oxidizes sulfide to sulfate and itself reduced to MnSO4, which is colorless. Barium sulfite plus sulfuric acid, barium sulfate and sulfur dioxide. Then Kamenever reacts with this sulfur dioxide and it is converted to MnSO4 and MnSO4 is colorless. That is why the potassium permanganate solution get decolorized. There are 2 confirmatory tests for nitrite anion. One is acidified potassium iodide plus starch test that we have already discussed. The second one is sulfanic acid test. It is also called sulfanic acid 1-naphthylamine reagent test or grease elosway test. For that, we take 1 ml of the extract acidified with acetic acid. To that, we are adding sulfanic acid solution drop by drop using a dropper. Now we add naphthylamine reagent drop by drop, and the color of the solution changes to red. And this red color is due to the formation of an azodide. The reaction can be represented in this way. The nitrite NO2 minus combined in presence of acetic acid, it is converted to nitrous acid. The nitrous acid combines with the sulfanic acid and forms diazotized acid. The diazotized acid now combines with the 1-naphthylamine giving red azodide. Next, we shall consider the preliminary test for another set of 4 anions, and these are chloride, bromide, iodide and nitrate. Here we use concentrated sulfuric acid. First, take chloride. To about 0.1 gram of the salt in a test tube, add a few drops of concentrated sulfuric acid and warm. Colorless pungent smelling gas which gives dense white fumes with ammonia is produced. This is concentrated sulfuric acid. We are adding a few drops of concentrated sulfuric acid. And we gently warm the solution. And some gas is coming out. And if you show a glass rod dipped in ammonium hydroxide, thick white fumes are produced. And these thick white fumes are due to the formation of ammonium chloride vapors. Suppose that you are given sodium chloride. Sodium chloride reacts with the sulfuric acid and generate HCl gas. And when you show ammonium hydroxide contain ammonia, and HCl and ammonia reacts together to give ammonium chloride. And this ammonium chloride vapors appear as thick white fumes. For testing bromide, take a little of the salt in a test tube and heat it with the concentrated sulfuric acid. Reddish brown fumes of bromine is evolved. And the formation of fumes get intensified on addition of manganese dioxide. So we take the solid salt and add some manganese dioxide. To that we are adding concentrated sulfuric acid drop by drop. And now we heat the solution. And red fumes are coming out. Thick red fumes are coming out and the solution turns red. Suppose that you are given sodium bromide. It reacts with the sulfuric acid releasing bromine. And this bromine has a red color. And if you add manganese dioxide, this is the reaction that is taking place. A large amount of bromine gas will be produced. Bromine turns starch potassium iodide paper blue-black. Bromine releases iodine from potassium iodide and the I3- formed in the reaction mixture shows a blue color with starch. Next, we consider the test for iodide. On heating with concentrated sulfuric acid, deep violet vapors with a pungent smell is evolved. It turns starch potassium iodide paper blue. With the manganese dioxide, dense white fumes are formed. So we take some salt in the test tube and to that some manganese dioxide is added. Now we add concentrated sulfuric acid drop by drop. And we heat the test tube. Dense violet fumes are coming out. Now let us introduce a starch potassium iodide paper into the test tube. And upon withdrawing it, it turns blue. Suppose that you are given sodium iodide, and sodium iodide in presence of manganese dioxide reacts with the sulfuric acid releasing iodine. And the iodine formed react with the starch iodide paper, starch potassium iodide paper, and it is turned blue in color due to the formation of a complex formed by I3 minus and starch. Now let us consider the test for nitrate ion. On heating with the concentrated sulfuric acid, light brown fumes are evolved. When some copper turnings, small pieces of copper, are added, dense brown fumes are evolved. The solution turns blue. So we take some of the solid salt along with some copper turnings. To that we are adding concentrated sulfuric acid. And after the addition of concentrated sulfuric acid, we heat the solution. And the reddish brown vapors are coming out. The color of the solution turns blue. Suppose that you are given sodium nitrate. Sodium nitrate reacts with the sulfuric acid and metallic copper, giving copper sulfate, sodium sulfate, and nitric oxide. And this copper sulfate is blue in color. Nitric oxide is converted to, further oxidized to nitrogen dioxide. And nitrogen dioxide shows the reddish brown color. Let us consider the confirmatory test for chloride, bromide, iodide, and nitrate ions. First take chloride. And for that we need sodium carbonate extract. A little of the extract is acidified with dilute nitric acid and a silver nitrate solution is added. We take about 1 ml of the extract. And this is dilute nitric acid. We add dilute nitric acid for acidification. It is followed by a few drops of silver nitrate solution. So we are adding silver nitrate solution. And we observe the formation of a curdy white precipitate. And this confirms the presence of chloride ion. Now, this is ammonium hydroxide. We add a few drops of ammonium hydroxide to that. And this is due to the formation of silver chloride. And silver chloride dissolves in ammonium hydroxide. So the confirmatory test for chloride is that when you add silver nitrate solution to a little of the acidified extract, a curdy white precipitate will be formed and it is completely soluble in ammonium hydroxide. Suppose that you are given sodium chloride. Sodium chloride reacts with the silver nitrate giving silver chloride, and this silver chloride appears as white curdy precipitate. When ammonium hydroxide is added, silver chloride forms a complex with it and which is soluble. And the complex formed is diamine silver 1 chloride. Now we consider bromide. So we use sodium carbonate extract for that. First we acidify extract with the dilute nitric acid and add silver nitrate solution. About 1 ml of the extract. To that dilute nitric acid is added drop by drop. And after that we add silver nitrate solution. Silver nitrate solution is slowly added and a precipitate which is having a pale yellow color is formed. A pale yellow precipitate is formed. And here also we add ammonium hydroxide. And we add ammonium hydroxide drop by drop. And let us see what happens. The precipitate is only partially soluble. It is not completely soluble in ammonium hydroxide, and that is a difference from chloride. For chloride, the precipitate is completely soluble in ammonium hydroxide, but for bromide, the precipitate is pale yellow in color and only partially soluble. And suppose that you are given sodium bromide and it reacts with the silver nitrate giving silver bromide, and this is having a pale yellow color. The next ion we have to consider is iodide. We take about 1 ml of the extract and as before acidify with the dilute nitric acid and a silver nitrate solution is added. So this is dilute nitric acid. Now we add silver nitrate solution. Yellow precipitate is formed. As before, we add ammonium hydroxide to the solution, but the precipitate is totally insoluble. So when we add silver nitrate, we get silver iodide, and a silver iodide forms the yellow precipitate. So we can distinguish between chloride, bromide and iodide using this test. For chloride, the white precipitate is silver chloride, which is completely soluble in ammonium hydroxide. For bromide, it is silver bromide and it is pale yellow in color and only partially soluble in ammonium hydroxide. For iodide, the precipitate is silver iodide, which is yellow in color and it is totally insoluble in ammonium hydroxide. To distinguish between bromide and iodide, we can use the layer test. First take bromide. 1 ml extract neutralized with the dilute hydrochloric acid. To that we are adding carbon tetrachloride, about 1 ml. Carbon tetrachloride is immiscible with water, so it must form 2 layers. And to that we are adding chlorine water. Chlorine water drop by drop. And now we close the test tube with a cork. And 2 layers are formed. And the bottom layer is the organic layer or the CCl4 layer. And the upper layer is the aqueous layer. And now we shake the test tube vigorously. As I said earlier, animations may not represent the exact situation. So here the organic layer become red. The aqueous layer also is slightly red. And this is due to the formation of bromine. Sodium from chlorine is able to displace sodium bromine from sodium bromide. And so that bromine is produced. And bromine is highly soluble in organic layer CCl4. So the CCl4 layer become red. This color should be red. And bromine is slightly soluble in water. So the aqueous layer also get a faint red color. So let us see how iodide respond to this test. As before, we take about 1 ml of the extract which is neutralized with a dilute hydrochloric acid. And to that we are adding about 1 ml CCl4 and it will form 2 separate layers and it is followed by chlorine water. And we close the test tube using a cork and shake it vigorously. So 2 layers are formed here. The upper layer is the aqueous layer and the bottom layer is the CCl4 layer, organic layer. Now we shake it well. So a violet color appears to the organic layer and a violet color is due to the liberation of iodine. Iodine is soluble in CCl4 but iodine is insoluble in aqueous layer, so the aqueous layer remains colorless. Next is the confirmatory test for nitrate ion and that is the brown ring test. For that we take about 1 ml of the extract which is acidified with the dilute sulfuric acid. Now we add an equal volume of ferrous sulfate to that. And we shake the solution well. And to that solution, we carefully add concentrated sulfuric acid through the sides of the test tube using a dropper. Without shaking, we are adding concentrated sulfuric acid. Now, gently turn the test tube in the upright position. A brown ring appears at the junction of the two liquids. And this brown ring shows the presence of nitrate. And suppose that you are given sodium nitrate and it reacts with the sulfuric acid giving nitric acid. Ferrous sulfate in presence of sulfuric acid reacts with the nitric acid, produces ferric sulfate and a nitric oxide. And the nitric oxide formed react with the ferrous sulfate giving nitrous of ferrous sulfate, and this nitrous of ferrous sulfate is brown in color. One more radical we have to consider, that is sulfate. And to 1 ml of the extract, we add barium chloride solution after acidification with a dilute HCl. So this is barium chloride solution. We add barium chloride solution drop by drop. A white precipitate is formed. So sodium sulfate plus barium chloride, we get barium sulfate, and barium sulfate is the white precipitate. And barium sulfate is insoluble in concentrated HCl or concentrated HNO3. But barium sulfite, SO3 2-, that is soluble in concentrated or dilute HCl. That is the difference between sulfite and sulfate. One more test is there. We take a little of the extract and acidify it with acetic acid. And to that we are adding lead acetate solution. And we get a white precipitate. And a white precipitate is due to the formation of lead sulfate. Lead sulfate is white in color. Let us discuss some multiple choice questions related to the topic you have studied, that is analysis of anions. Question 1. A salt dissolves in a particular solvent when option 1, solvation enthalpy is equal to lattice enthalpy. 2, solvation enthalpy is less than lattice enthalpy. 3, solvation enthalpy is greater than lattice enthalpy. 4, solvation enthalpy is approximately equal to lattice enthalpy. And first let us see what is meant by solvation enthalpy and lattice enthalpy. Lattice enthalpy is related to the strong forces of attraction between the ions of a salt. For a salt to dissolve in a solvent, these strong forces must be overcome by the ion-solvent interactions. Solvation enthalpy of ions is the energy released in the process of solvation. It depends on the nature of the solvent. Therefore, a salt dissolves in a particular solvent when solvation enthalpy is greater than the lattice enthalpy. So therefore, option 3 is the correct answer. Yes, that is a correct answer. Question number 2. An electrolyte precipitates when ionic product exceeds solubility product. Solubility product exceed ionic product. Ionic product become equal to solubility product. The solution is heated. Now, an electrolyte precipitates when the ionic product exceeds solubility product. So we go for option 1. That is the correct answer. Let us consider an example. Saturated solution of barium sulfate in water. There exists an equilibrium between the solid barium sulfate and a dissolved barium sulfate, that is Ba2+ and SO4 2-. The solubility product Ksp is the product of concentration of barium 2+ and SO4 2-. An electrolyte precipitates when the concentration of the ions, that is, the ionic product, in solution exceeds the solubility product at a given temperature. Question number 3. Which of the following sets of anions can be detected with the help of dilute sulfuric acid? Option 1, option 2, option 3, option 4. And we know that dilute sulfuric acid is used as a preliminary test for carbonate, sulfite and nitrite. Therefore, option 4 should be the correct answer. Yes, that is the correct answer. Question 4. When an inorganic compound is heated with the dilute sulfuric acid, colorless gas with the smell of rotten eggs evolved and that turned lead acetate paper black. The compound may be sodium carbonate, sodium sulfite and sodium sulfide. Fourth option, sodium nitrite. And we know that the gas with the smell of rotten eggs is hydrogen sulfide. So therefore, we can eliminate option 1 and option 4. And the sulfate will not release hydrogen sulfide. So option 2 also is wrong. Hence the correct option must be the third option, that is sodium sulfide. Sulfides, when heated with the dilute sulfuric acid, produce hydrogen sulfide, which is having the smell of rotten eggs. With the lead acetate, it produces lead sulfide, which is black in color. Question number 5. When excess carbon dioxide is passed through lime water, the milkiness produced initially disappears due to the formation of calcium carbonate, calcium oxide, calcium hydrogen carbonate, calcium hydroxide. When excess carbon dioxide is passed through lime water, the milkiness disappears. And this is due to the formation of calcium hydrogen carbonate. So the third option is the correct answer. Lime water is calcium hydroxide. When carbon dioxide is passed through it, calcium carbonate precipitate. And this calcium carbonate causes milkiness. When we go on passing carbon dioxide, the calcium carbonate formed react with the carbon dioxide and producing calcium hydrogen carbonate, that is soluble. Question number 6. Lime water is a solution of barium hydroxide, a clear solution of calcium hydroxide, a clear citrus juice, a solution of calcium chloride. And lime water is a clear solution of calcium hydroxide. So option 2 is the correct answer. A clear solution of barium hydroxide is called baryta water. It also turns milky when carbon dioxide is passed through it due to the formation of barium carbonate. Question 7. The gas with the smell of burning sulfur is sulfur trioxide, sulfur dioxide, nitrogen dioxide, nitric acid. We can eliminate option 3 and 4. So the correct answer is sulfur dioxide. Sulfur dioxide is having the smell of burning sulfur. So sulfur dioxide is the correct answer. Question number 8. When sodium nitrite is heated with the dilute sulfuric acid, brown fumes are evolved. It is due to sulfur dioxide, nitrogen dioxide, nitrous oxide and nitric acid. And we know nitric oxide and nitrous oxide, sulfur dioxide, etc. are colorless gases. And nitrogen dioxide is brown in color. So that is the correct option. Sodium nitrite, when heated with the sulfuric acid, it generates nitrous acid. And a nitrous acid decomposes giving nitric oxide. And the nitric acid is colorless. Nitric oxide further undergo oxidation to give nitrogen dioxide, which is a brown gas. Question number 9. Which of the following salt has the lowest solubility product, KSP? NH4Cl, AlCl3, AgCl, BaCl2. And among these, except AgCl, all others are soluble in water. And Ksp for AgCl is 1.8 into 10 raised to minus 10. So the correct option is 3. When a salt is heated with dilute sulfuric acid, a colorless gas evolved. When this gas is passed through acidified potassium dichromate solution, it turned green. The salt taken and the gas produced may be 1. Sodium carbonate and carbon dioxide, sodium sulfate and sulfur dioxide, sodium sulfate and hydrogen sulfide, sodium sulfite and sulfur dioxide. And we can eliminate the first option because carbon dioxide will not form green color. And here sulfur dioxide may be the gas, but it will not be produced by heating sodium sulfate. So that option is also wrong. And when sodium sulfite is heated, we do not get hydrogen sulfide. So that also is wrong. So the correct option will be the fourth one. Sodium sulfite plus sulfuric acid, sulfur dioxide gas is produced. When it is passed through acidified potassium dichromate is converted to chromium sulfate. And this chromium sulfate is green in color. A student added a few drops of sodium nitroprusside to 1 ml sodium carbonate extract of an unknown salt. A purple color is observed. The anion confirmed in the given salt will be option 1 sulfite, option 2 sulfide, option 3 sulfate, and option 4 nitrite. And we know sodium nitroprusside test is for the sulfide ion. So second option will be the correct answer. Yes. Suppose we are given sodium sulfide and this is sodium nitroprusside and this is sodium thionitroprusside which is purple in color. Question number 12. Aqueous solution containing which of the following anions will decolorize acidified potassium permanganate solution? Option 1 carbonate, 2 sulfate, 3 nitrate and 4 sulfite. Just have a look at the oxidation state of the central atoms of these ions. Carbon is in the +4 oxidation state. Sulfur in sulfate is in the +6 oxidation state. Nitrogen in nitrite is +5 oxidation state. Sulfur in sulfite is in +4 oxidation state. Except sulfite, all are in their possible highest oxidation state. Hence cannot be further oxidized by permanganate and no decolorization is observed. Hence the correct answer will be option 4. Question 13. To about 1 ml of water extract of an inorganic salt, barium chloride solution is added. A white precipitate is produced which dissolves in dilute Cl, producing a gas with the smell of burning sulfur. The anion present in the salt will be 1 sulfite, sulfate, sulfide and nitrate. So we can eliminate nitrite. Nitrite, that is a wrong answer. Also we can eliminate 3, that also is wrong. And we know sulfite as well as sulfate give white precipitate with barium chloride. For sulfate it is barium sulfate and barium sulfate is insoluble even in concentrated HCl. So here the precipitate dissolves in dilute HCl. So we can eliminate option 2 also. Hence the correct answer is option 1, that is sulfite. Sodium sulfite plus barium chloride we get barium sulfite, it is the white precipitate. But when we add dilute HCl, it dissolves and produces sulfur dioxide gas. And sulfur dioxide gas is having the smell of burning sulfur. Question 14. Barium chloride is added to 1 ml of the water extract of an inorganic salt. A white precipitate is formed. When few drops of acidified potassium permanganate solution is added, it got decolorized. Which of the following may be the given compound? Sodium sulfate, ammonium sulfate, calcium sulfite, sodium sulfite. Of course, the precipitate decolorizes KMnO4. So we can eliminate sodium sulfite and ammonium sulfate. So these two options we can eliminate. And sulfite reacts with the barium chloride, giving barium sulfate, which is further oxidized by KMnO4. So sodium sulfate is capable of reducing potassium permanganate or decolorizing potassium permanganate. So the answer should be the fourth one. That is the correct answer. Barium sulfite gives sulfur dioxide, and potassium permanganate oxidizes sulfur dioxide to sulfate. Here calcium sulfite is there, but we choose sodium sulfite. This is because the solubility of calcium sulfite is very low in water. So the sulfites of sodium, potassium and ammonium are soluble in water. The solubility of calcium sulfate in water is low. Question number 15. A filter paper moistened with a starch solution containing potassium iodide and acetic acid turned blue when exposed to a particular gas. The gas may be carbon dioxide, hydrogen, nitric oxide and nitrogen dioxide. We can definitely eliminate first and second option. Nitrogen dioxide dissolves in water to give nitrous acid, which liberates iodine from potassium iodide. And iodine gives a blue color with a starch solution. So we can choose fourth option, that is the correct option. Nitrogen dioxide dissolves in water giving nitrous acid. Nitrous acid converts I- to iodine. Iodine make a complex with the starch and which is blue in color. Question number 16. When an inorganic salt is formed with the dilute sulfuric acid, reddish brown fumes are evolved. When potassium iodide is added to the solution followed by acidification with acetic acid, produced blue color. The salt may be 1. Sodium nitrate, sodium nitrite, sodium chloride and sodium sulfate. So we can eliminate option 4 as well as option 3. And we can also eliminate option 1, sodium nitrate also. And we know sodium nitrite produces nitrous acid and which oxidizes I-2 iodine. So NaNO2 will be the correct answer. So sodium nitrite reacts with the sulfuric acid giving sodium sulfate and nitrous acid. And the nitrous acid formed reacts with the potassium iodide in presence of acetic acid, generates iodine. Iodine combines with the starch giving a blue complex. Question number 17. A student observed evolution of a colorless gas when dilute sulfuric acid is added to the given salt. The gas turned lime water milky. When a few drops of acidified potassium permanganate solution is added, it got decolorized. The given salt may be sodium carbonate, sodium sulfite, sodium nitrite, none of the above. We may choose option 1 as the correct answer, but that is not the correct answer. Since KMnO4 is decolorized, it cannot be a carbonate. Also, it cannot be sodium nitrite because sodium nitrite gives brown fumes. So, option 2 should be the correct answer. Sulfides, when treated with dilute sulfuric acid, produces sulfur dioxide gas, and it turns lime water milky due to the formation of calcium sulfate. And a calcium sulfite, CaSO3, reduces potassium permanganate and a decolorization occurs. Nitrites produce nitric oxide and nitrogen dioxide, but it is brown in color. So that is not the correct answer. Question number 18. When an unknown given salt is treated with concentrated sulfuric acid and manganese dioxide powder, copious evolution of reddish brown gas is observed and the solution turned red. The anion present may be nitrite, bromide, and a fourth option, iodide. And we know that concentrated sulfuric acid produce bromine when reacted with the bromides. So the correct option should be the third one, that is bromide. For example, sodium bromide in presence of manganese dioxide and concentrated sulfuric acid produces bromine gas. Question 19. A student observed evolution of brown fumes when concentrated sulfuric acid is added to the given unknown salt. When some metal scraps are added, dense evolution of brown fumes is observed and the solution becomes colored. The metal scrap added and the color developed are 1. Aluminium and color red, zinc blue, copper red, copper blue. And we know that when nitrates, when heated with concentrated sulfuric acid, in presence of copper turnings, that small pieces of copper, it is converted to copper sulfate and nitric oxide is produced. Nitric oxide first further undergo oxidation to give nitrogen dioxide, which is brown in color. And the blue color is due to the formation of copper sulfate. So the correct answer should be the fourth option, that is copper and a blue color. This reaction is used as a test for nitrates. Question 20. When an inorganic salt is treated with concentrated sulfuric acid and manganese dioxide, dense fumes of violet color appeared and violet sublimates are formed on the sides of the test tube. When a starch paper is introduced into the gas, the paper turned blue. The substance taken may be sodium chloride, sodium bromide, sodium nitrite, sodium iodide. We know that iodine turns acidified starch potassium iodide paper blue. So the answer should be the fourth option. So sodium iodide plus sulfuric acid, sodium sulfate and sulfur dioxide gas. Along with that, iodine is produced. And the violet sublimate is due to the solid iodine that condenses on the sides of the test tube. Question 21. When sodium nitrate is treated with concentrated sulfuric acid and copper turnings, copious evolution of brown gas occurred and the solution turned blue. The color is due to 1. Formation of copper sulfate, formation of iodine, formation of cupric oxide, formation of copper nitrate. So sodium nitrite, when heated with concentrated sulfuric acid and copper turnings, small pieces of copper sulfate is produced and a copper sulfate is blue in color. The nitric oxide gets oxidized to nitrogen dioxide, which is brown in color, brown fumes. So option 1 is the correct answer. Question number 22. When an unknown substance is treated with concentrated sulfuric acid, a pungent smelling gas is produced. When a glass rod dipped in a particular solution is shown at the mouth of the test tube, produced a dense wet fumes. The solution on the glass rod is 1. Sodium hydroxide, ammonium hydroxide, sodium chloride, and 4 ammonium chloride. The dense white fumes is due to ammonium chloride. So the answer should be the second option. That is, sodium chloride, when treated with a concentrated sulfuric acid, iodine chloride gas is produced. When ammonium hydroxide is introduced, HCl reacts with the ammonia and ammonium chloride vapors are formed, and these ammonium chloride vapors appear as dense white fume. Question 23. Grease-Ilonsway test is used as a confirmatory test for which of the following anions? Nitrate, sulfite, chloride, nitrite. This test is also known as sulfanylic acid 1-naphthylamine test. This test is used as a confirmatory test for the nitrite ion, and that is the correct answer. When sulfanylic acid is added to nitrite solution acidified with acetic acid, the sulfanylic acid gets diazotized with the nitrous acid produced. The diazotized acid couples with 1-naphthylamine to form a red azo dye, and it is used as a confirmatory test for nitrite. The sulfanylic acid 1-naphthylamine reagent test is also called Grease-Ilonsway test. Question number 24. Two statements are given here. When selenitrated solution is added to 1 ml aqueous solution of potassium chloride acidified with dilute nitric acid, a curdy white precipitate partially soluble in ammonium hydroxide is formed. Statement 2. Chlorides produce thick white precipitate of silver chloride with silver nitrate, which is completely soluble in ammonium hydroxide due to the formation of AgNH3 twice Cl. Option 1. Both statements 1 and 2 are true. Option 2. Both statements 1 and 2 are false. Option 3. Statement 1 is true, but 2 is false. Statement 1 is false, but 2 is true. And statement 1 is, when selenitrate solution is added to 1 ml aqueous solution of potassium chloride acidified with dilute nitric acid, a curdy white precipitate partially soluble in ammonium hydroxide is formed. The curdy white precipitate is due to the presence of silver chloride, but it is completely soluble in ammonium hydroxide. So statement 1 may be wrong. Now chlorides produce thick white precipitate of silver chloride with silver nitrate, which is completely soluble in ammonium hydroxide due to formation of the silveramine complex. So statement 2 is correct. So the correct option is option 4. That is the correct answer. Question number 25. About 1 ml of the extract is acidified with dilute sulfuric acid and a few drops of dilute KMnO4 solution is added. Immediate decolorization indicates the presence of which of the following ions? Sulfide, sulfite, sulfate, Br-, nitrate, I-. Option 1, option 2, option 3, option 4. And option 1 include sulfate, and we know that sulfate will not decolorize potassium permanganate, so we can eliminate that. And in the second option also sulfate is there. And in the third option, nitrate, and a nitrate cannot be further oxidized, that also may be eliminated. Hence the correct answer is option 4. Sulfide, sulfite, bromide, iodide, all are reducing agents which decolorize potassium permanganate. Question number 26. The anion that can be confirmed by sodium nitroprusside test is sulfite, bromide, sulfide, nitrite. And that is the test for sulfide ion. That is the correct answer. Sodium sulfide, for example, reacts with the sodium nitroprusside, giving a purple colored complex. The confirmatory test for nitrate is brown ring test. The brown ring is due to the formation of option 1, option 2 and option 3. And the brown ring test is due to the formation of nitrous of ferrous sulfate, which is brown in color. So option 4 is the correct answer. Question number 28. The layer test is used to distinguish between bromide and iodide, nitrite and nitrate, sulfate and sulfate, sulfate and thiosulfate. And layer test is used to distinguish between bromide and iodine. It is done in the following way. To about 1 ml of the water extract, add an equal volume of CCl4. Add excess chlorine water and shake well. The CCl4 layer becomes red if bromide is present and violet if iodide is present. Sodium bromide plus chlorine. Chlorine displaces bromine. Similarly, chlorine displaces iodine from sodium iodide. Question number 29. It is an assertion reason type question. Assertion. The anions of sulfite and sulfate could not be distinguished using barium chloride test. Reason. Sulfites from barium sulfite and sulfates from barium sulfate. Both are soluble in HCl. Option 1. Both assertion and reason are correct, and the reason is the correct explanation of assertion. Option 2, option 3 and option 4. Sulfites from barium sulfate, which is soluble in dilute HCl, and sulfates from barium sulfate, which is insoluble even in concentrated HCl. So assertion, the anions sulfite and sulfate could not be distinguished using barium chloride. That is wrong. That we can distinguish because barium sulfite is dissolved in dilute HCl and barium sulfate is insoluble. Similarly, reason sulfites from barium sulfate and sulfates from barium sulfate both are soluble in HCl. Only barium sulfite is soluble. Hence, assertion as well as reason are wrong. So, option 4 is the correct answer. Question number 30. That also is an assertion reason type question. Assertion, it is important to store selenitrate solution in dark colored bottles. Reason, in presence of light, selenitrate decompose forming silver. Dark colored bottles prevent passage of light. 1. Both assertion and reason are correct, and reason is the correct explanation. Both assertion and reason are correct, but reason is not the correct explanation. Assertion incorrect, reason correct, assertion correct, but reason incorrect. It is true that we are keeping selenitrate in dark colored bottles. The reason is, in the presence of light, selenitrate decompose forming silver. So, option 1 is the correct answer. That is the correct answer. Silver nitrate decomposes giving silver and nitrogen dioxide and oxygen.